Professor Tatsuya. He received his PhD from Graduate School of Science, University of Tokyo, and later joined in Hokkaido University and moved to Tokyo University as professor. He's an eminent scientist and recipient of various awards like Inouye Research Encouragement Award, Chemical Society of Japan Academy Award, and also he have over 230 publications, and is a fellow of Royal Society of Chemistry and senior editor of Journal of Physical Science, Physical Chemistry Letters. With this brief introduction, I request Professor Tsukuda to deliver his lecture on chemically modified gold superatoms. Professor Tsukuda, it's you too, sir.
You are muted, Tatsuya. Yeah, okay, now. Oh, just went away. Yes.
Okay, thank you very much. Thank you very much for the kind introduction. I'm Tatsuya Tsukuda from Tokyo University. First of all, I want to thank the organizers and Professor Pradeep for inviting me to this symposium. Thank you. It's a pity that I couldn't meet you in person, but I'm very happy that I can contribute to this special event for students and young researchers. Okay, so in the next 30 minutes, I will be talking about some low-tech nanochemistry on tiny metal particles. Okay, before starting my talk, let me thank my coworkers. And this is the picture of my group. And you can see the group size is much smaller than Professor Pradeep's group, but this is comfortable for me. But anyway, the main players are Professor Takano and Professor Koyasu and Professor Masuda. Okay, so and other PhD students. And also, before starting my talk, let me share some pictures. I met Professor Pradeep nearly 15 years ago in Japan, and since then, he has been always next to me, and he always continuously support me and guide me. And recently, he got the award from Japanese newspaper company for purification of water. And I want to thank him for his continuous support and guidance and friendship. And also you can see some speakers, Professor Wetten, Professor Shea in this picture. Okay, so let me start my scientific part. Okay. Our target, research target is very small clusters, particles, which we call clusters. And as you know, if you think about the atomic packing of nanoparticles, okay, here, the atomic packing is quite similar to the bulk packing. And so you can say that nanoparticles can be viewed as a small fragment of the bulk metal. And their properties can be scalable by thinking about the dimension of the particles. But if you go smaller, below 2 nanometer or less than 100 atoms, the situation will be changed dramatically. In the case of clusters, atomic packing is quite different from bulk metals. For example, they can form icosahedral packing, which has 5-fold symmetry. So this packing cannot be achieved in the bulk. And also the electronic structures of such small clusters are well quantized. So basically they are not metal anymore. So we can expect some unusual properties in such small regime. So we are interested in these kind of clusters protected by organic ligands or weakly stabilized by polymers or immobilized on the solid materials. So these are our target. And we focused on gold clusters because there are so many fundamental knowledge accumulated for this system by using a molecular beam technique. So we know that the gold clusters with the size of 20, 34, 58 are very stable. We call these numbers as magic numbers. And if you solve the Schrödinger equation by assuming this kind of potential, which are between harmonic and square well potential in the quantum chemistry textbook, you have these discrete orbitals. And if you fill the orbitals with these number of electrons, you can close the electric shell. Because these numbers and these magic sizes are the same, we can say that the stability of gold clusters are explained by the closure of the electric shell. And this simple idea has been proved by Professor Smalley, a Nobel Prize winner for the discovery of fluorine. And these measurement for electron affinity can support this simple idea. And more interestingly, the properties of gold clusters, such as chemical reactivity, can be also related to electronic structures. You can see the mirror image between reactivity and the electron affinity. So in the case of gold clusters, electric structures govern stability and many properties. So the explanation can be very simple in case of gold. So that's the reason why we focus on gold. Okay, so then, these clusters are isolated in vacuum. But in order to make it as a chemical compound, we have to protect the surface with the ligands to suppress the sintering into larger particles. So the most famous ligands we use is that thiol, sulfur-containing molecules. This is because we know the sulfur molecules spontaneously form self-assembled monolayer like this onto gold surface. So the gold sulfur is a very, very strong is a very strong interaction. And this idea has been applied for nanoparticles by Professor Blast and Schifrin in 1994. And the Professor Wetten, who is the speaker of the next tomorrow's session, discovered there are several series of magic clusters in thiol-protected gold clusters. And the Professor Murray showed that the charging behavior of such small clusters are molecular-like. They are not metal anymore. So after this kind of pioneering work, we tried to synthesize these clusters with atomic precision. So we want to avoid distribution in size. So how can we synthesize these thiol-protected gold clusters? So we established this synthetic method 15 years ago. And the method is composed of 3 steps. The first step is the reduction of metal ions in the presence of thiol. And after some etching treatment, we have a mixture of stable clusters in solution. So then next step is the fractionation of these mixtures by size using this separation technique. Okay, then after that, after this separation, we have a series of clusters like this from brownish mixture. And then the last step is the determination of the molecular formula of the cluster compound in individual solutions by using ESI mass spectrometry, which Professor Pradeep explained to you. So this is a non-destructive method to determine the molecular weight of the cluster compound in solution. And for example, by analyzing this kind of data, we can say that the clusters is contained of 25 gold atoms and 18 thiolate ligands. So we can determine chemical composition of individual solution. Okay, so we have a method to synthesize the clusters with atomic resolution. And the next question is the structure of the clusters. And Professor Kornberg determined the structure of this kind of thiolate-protected clusters by single crystal X-ray diffraction. And he discovered that 79 gold atoms out of 102 form this kind of highly symmetrical core, and other gold atoms are located on the surface, forming sulfur gold sulfur small oligomers on the surface, and which we call staples. So now we understand the core is protected by these kind of short oligomers in the case of thiol. So we can determine the structure by single crystal XRD if you can crystallize them. Okay. And then what about the electric structures? And the electrical structures have been studied theoretically extensively. And here is one example. This is gold 25 thiol 18 minus. And this is structures of single crystal structures of this compound. And you can see the core is composed of 13 ixohedral gold atom. And if you and this core has these kind of discrete orbitals. And in this case, we have 8 electrons confined in this core. And these 8 electrons are accommodated into S-like orbitals. You can see 1s has this kind of shape. And we have 3 p orbitals here. And these orbitals are occupied by 6 electrons. And p orbitals looks like this. So there is a nice similarity between atomic orbitals and the orbitals in the clusters. So then we call these clusters as superatom. Okay, so there's a beautiful correlation between atoms and the gold clusters. So these are the backgrounds, and so then I think that the gold clusters protected by organic ligands can be viewed as chemically modified superatoms. The surface is modified by chemical compound, and we can use a variety of ligands, including carbene, phosphine, thiol, and alkenyl. So a variety of ligands can be used to protect the gold clusters, and we call these species as chemically modified superatoms. What I wanted to talk today is about the correlation between the structures and the properties, okay, of this kind of species. And the structure parameters include the core size, okay, and the chemical composition of the core, and the shape or atomic packing of the core. And also the nature of the ligands is another important structure parameter. So I would like to show you some examples how these structure parameters, size, composition, shape, surface modification affects the properties of this kind of system. And finally, I would like to talk about new synthetic methods of superatom-based materials at the end. Okay, let me first start with the size effect on the properties. Okay, so here is a series of mass spec for the thiol-protected gold clusters. TT means dodecan thiol. So we can determine a chemical composition like this by using ESI mass spectrum. Okay, and then we measure optical absorption spectra for these clusters. So here is a optical absorption spectra for the series of clusters we isolated. And as you can see, this band, which we call localized surface plasmon resonance band, disappears when we go below 187. So this band, it comes from the collective oscillation of the electrons in the core. So if you see this band, you can say this particle is metallic. So absence of this band below 87 means that these clusters are not metal. And actually, you can see some discrete sharp structures. So this means the electronic structures are quantized. So metal to non-metal transition takes place at this critical size. So this is a very fundamentally important and interesting question we can address by size selective synthesis. And after that, our community discovered that these metallic cores, gold and silver cores, are formed within the organic layer. And if you count the number of electrons confined in these cores, 2, 8, 58, and so on, these numbers can be explained by the closure of the superatomic orbitals, okay, as I told you in this case. Okay, in the case of 58, these orbitals are occupied by 58 electrons. But these largest particles, electrons number is not good cannot be explained by a simple closure of the electric shell. So the conclusion of this page is that when the cluster size are small enough, again, the electric shell closure is a main important parameter to explain the stability. But for these clusters, atomic packing governs the stability of the whole system. Okay, let me move on to the second topic, composition effect on the properties. So we can dope some foreign element into the clusters and see what happens by this doping. Today I will talk about a single atom doping to icosahedral gold-13 clusters. Okay. Here is one example. So we can synthesize ruthenium-doped gold clusters. Okay. The surface is a phosphine ligands, but you can ignore this outer layer. You can focus on this core. And the core is made of ruthenium-centered gold-12 icosahedral packing. And this cluster has this kind of optical absorption spectra and exhibit intense photoluminescence, red light intense emission. And the quantum yield is nearly 40%. This is quite large numbers. Okay, so these clusters can emit light with high efficiency. And interestingly, this luminescence can be quenched by the presence of oxygen. So oxygen can quench this emission. So this means that this emission can be assigned as a phosphorescence. Okay, so this is a very efficient photofluorescence clusters. And if you reduce the temperature, the origin of the photoluminescence is changed to fluorescence. Okay, but anyway, single atom doping can enhance the quantum yield of photoluminescence dramatically. And we are now extending this approach to other elements. And if we dope platinum, iridium into the gold-13 core, we can enhance the photoluminescence quantum yield above 60%. So this is really bright particles. So single atom doping can modulate the photophysical properties like this. Okay, so then the third topic is about the effect of shape. So of course, atom cannot change the form, but if it is superatom is composed of several atoms, so we can change the shape of the superatom. So here I show you one example, prolate, like superatoms, elongated shape. And we could synthesize two types of prolate superatoms. The first one is gold-38 thiol-24. This is a mass spec. You can see purity of the sample, and theoretical prediction and the single crystal XRD data appeared nearly the same time. And both results shows that the core is made of 23 atoms, and it is composed of 2 icosahedron, sharing 3 atoms. And this one is another example. Gold 25 clusters protected by 3 types of ligands. So of course you can ignore the ligands. So you can see 2 icosahedrons are sharing single atom. So the number of cores is 25. Okay, so this is a single crystal structure. Okay, so this type of structure can be viewed as quasi-molecule made of superatomic gold-13 superatoms. So let me explain this. Okay, so by using the conventional superatomic concept, prolate superatoms may have this kind of electronic structures. Because of the deformation, the p orbitals and the d orbitals become non-degenerated, and they are split in energy like this. And the 14 electrons are good numbers for the deformed superatom. But this can be viewed in different way, like this. So we have 2 superatoms with 7 electrons. So this looks like halogen. Okay, 1 electron is missing. And they form a molecular orbital like orbitals like this. And 14 electrons are accommodated into these orbitals. And this bonding scheme, these orbitals are very similar with these. So this is another way of explaining the electronic structures of gold 23 core. Okay, and this corresponds to F2 in the conventional molecule. So the bonding scheme is very similar. And here is another example of superatomic molecules. So we call this as a superatomic molecules. So this is a di-superatomic molecules, like a diatomic molecules. So here's another smaller examples. So when we use this ligand, we can get these structures. And if you focus on the core, you can see this structure. And this core can be viewed as a helium dimer, like a helium dimer analog of a superatomic molecule. And if we use more bulky ligands, we can get this. And if you look at the framework, you can see this very unique structure. So gold trimer form a pair, and the core, gold 6 core, cannot be viewed as octahedral. It's a highly deformed, and we can see this pair is not bonded each other. As you can see here, there's no overlap in the orbital. So the bonding between 3 gold trimer is very weak in this case. So we think that this core can be viewed as a helium atom pair who's without any strong bonding. And this is due to the steric repulsion of the bulky ligands. Okay, so maybe skip. We can also synthesize a little bit thicker wire structure like this. And the high resolution TEM image show that the structure is composed of this kind of spherical FCC packing. And interestingly, this nanorod, very thin nanorod, shows a very intense absorption band like this. And these bands are localized surface plasma along the long axis. So the electrons in the rod can oscillate collectively along the long axis. And the position depends on the length of the rod like this. Okay, also, how much time do I have? 9. So let me go to the, how much time?
You have 10 more minutes, sir.
10 more minutes, including discussion.
No.
Okay.
5 minutes for a discussion.
Okay, so 10 minutes for talk. Okay, so let me talk about the surface modification effect. If we change the ligands, I will not go into the details. Anyway, we change the ligands, but the core is always 13. But the optical spectrum changes dramatically. So this means that the ligands not only suppress the aggregation, but also affects the electronic structures. Okay. So I will show you some example how the ligands affect the properties and the stability of the system. And gold 11 clusters is another famous superatom, which are protected by phosphine, but they are very unstable in solution. But if we replace one of the phosphine with this carbene, the stability can be enhanced dramatically. So single replacement of a single ligand can enhance the stability dramatically. And if we fully replace the ligands with carbene, the stability can be enhanced much more, and photoluminescence quantum yield can be enhanced dramatically, up to 16%. So carbene is promising ligands to stabilize the system clusters. And if we use the chiral ligands, like BINAP and others, you can induce CD activity, chiroptical activity, because maybe the core is deformed in chiral form by using these chiral ligands. And the photoluminescence quantum yield can be also affected by, enhanced by replacing the ligands. So in this case, we replace this ligand with much bulky ligands, but while retaining the core structure. But the photoluminescence quantum is enhanced dramatically. And we believe that this is due to the rigidification of the core by taking advantage of the ligand-ligand interaction. There are van der Waals or pi-pi interaction. This kind of interaction can rigidify the core and suppress the non-radiative decay from the photoexcited state. So the ligands can tune the properties like this. Okay, because of time limitation. So let me talk about this. And so far, all the surface atoms are protected by organic ligands. So there are no naked area. So this means that the catalytic reactivity must be very low, too stable. So in order to use these superatoms for catalytic process, we have to expose some of the surface for the substrate. And we use polymer, linear polymer, to stabilize the clusters, superatoms, like this. And our previous study shows that the small gold clusters are acting as a highly active catalysis for oxidation reaction. Although, gold is very inert, chemically inert, but when you reduce the size of the clusters down to 1 nanometer, they act as a catalyst for oxidation reaction. And recently, we can control the size of the clusters with atomic resolution. Now we can synthesize gold 24 clusters, and we are studying the structures by using high resolution TEM image and theoretical calculations. And we found that the structures are very flexible. Okay, so they are not rigid metal, but they are very, very fractional. Okay. Okay, the last topic is about the synthesis, development of new synthesis of superatomic based materials. So in previous studies, we know that the hydrogen and the gold behave similarly. So hydrogen mimic gold. So we try to dope hydrogen to gold clusters. Okay, so we can dope hydrogen atom to this gold cluster, gold 9 clusters, because at the center, there is a naked gold atom. So we can dope one hydride, H- species onto the center. Then we can detect such species. And if we calculate the electronic structures, after hydride doping, the core becomes more spherical and the p orbitals becomes degenerate. Okay, so it becomes more spherical, quasi-spherical system. And these hydride dope species are very active for further reactions. After hydride doping, and the cluster becomes very reactive, and then we can induce variety of chemical reactions with high efficiency. So we can dope other elements. Regiospecifically, regioselective doping can be possible. And we can also change the whole ligands with different one. And the efficiency is very large. So we believe this approach is very promising for target synthesis and large-scale synthesis of superatoms. And by using this approach, now we can fuse two superatoms into one. So we can make dimers starting from monomers by hydride doping process. And we are discussing the bonding scheme between two superatoms. Okay, this is the last slide. So I hope I can convince you that superatoms are artificial element in nanoscale. And we are interested in making a kind of periodic table by introducing a new coordinate of number of electrons. But the superatoms has a more variety of parameters like size, shape, doping, and so on. And in the future, I hope that these superatoms can be used as a building unit of making these kind of molecules and highly ordered structures. And I hope we can enjoy chemistry in a different level. So that's all. Thank you very much. And I'm happy to answer your questions.
Thank you, Professor Tsukuda, for the enlightening lecture on protected gold clusters. And you beautifully explained its structural aspects and also that hybrid mediated transformation. It was a nice talk.
Thank you very much.
Dear participants, you can share your questions. Professor Pradeep, it's your area, I think.
Yeah, we are collaborators, and he is such a, pioneering worker in this area. Yes, he's done a huge amount of work. He has done excellent stuff, and as you can see, every year he's doing excellent things. Well, let me ask one question for Tatsuya. So, what is the origin of this luminescence from ruthenium to change it to platinum? How do you understand that?
So you're asking why the doping can enhance the?
Oh, yes, and also the change between the elements.
All right. So far we have no clear explanation, but by doping these elements, we know that the HOMO-LUMO gap gradually increases. So according to energy gap law, the quantum yield can be slightly enhanced. So this is the only explanation we have. So, but there is no clear explanation for the doping effect of the photoluminescence quantum yield.
We are all in the similar situation. To fully know it, we have big challenges. But I wanted to know what your thoughts are. Also, the oxygen binding. Do we have a bound state of oxygen with oxygen?
You mean the we didn't see the complex of oxygen and the clusters, for example, by using ESI. So, so the binding is not
response in the photoluminescence response you talked about.
Yeah.
Sensitivity and all that. So, is there any transient possible? I mean, a state possible?
Yeah. Oxygen. We observe the formation of singlet oxygen. So energy transfer is very efficient from the T1 state of the clusters to triplet oxygen. So this quenching is very effective. So
Yeah. I see Janping raising his
jumping.
hand.
Oh, good to see you.
Professor Tsukuda, very nice talk. Always.
Thank you very much.
Okay, can you go to the next slide? I have same questions as Professor Pradeep. So how can you dope the one leucinium into the center of this AU12?
Yeah, basically there are many methods we apply. The most simple one is a co-reduction.
Co-reduction.
And as you know, some of the clusters contain two dopants, some of them does not. So we have to purify them after that.
Okay.
But in some cases, we can use the hydride dope method. So in that case, we can start with the palladium platinum centered gold. Then we can fully convert this cluster into doped cluster. So the yield is very high in such cases. 100 milligram scale in a pure form is easily achieved by using hydride dope approach. But in some cases, we have to use a conventional co-reduction method.
Yeah, cause this these several methods, they may have the different radius, right, for the actants, right? Platinum and leucinium, they are very different. So how can this different size of the metal atom go inside your AU13, right?
Yeah, actually, when the size is reduced, the packing of the gold, it becomes more comfortable. We see the change in the length after doping a smaller dopant. So maybe that will also rigidify the core to suppress the non-radiative process.
So will at least like contribute to the different luminescence properties of your cluster? Like the emission wavelengths are quite different, right?
Yeah, quite different. I'm not sure this is quite different or similar.
From 600 nanometer to 800 nanometer is just like.
But as I told you, homo-LUMO gap also changes gradually. But then nature is, LUMO is 1D, HOMO is 1P. So.
Okay, thank you. Very nice.
Thank you very much.
Thank you.
Thank you, Professor Jiamping and Professor Pradeep. And I express our sincere gratitude and appreciation to Professor Tsukuda for being with us and supporting EFCS 2021.
Thank you very much.
Now it's time for a break of 1 hour.
No, you need to present the memento.
Yes, sir. Professor, this is a token of love.
It is not, we can't see it, we can't see it. You'll have to show it well.
I can see.
Okay, good.
Thank you very much.
We will send it to you, Tatsuya.
Thank you very much.
Okay, thank you, sir.